A to D converter or analog to digital converter. So this converter converts analog input into digital output. So this is the basic block diagram of ADC or analog to digital converter. D equal to D1 2 power minus 1 plus D2 2 power minus 2 plus etc. Dn 2 power minus n, where D1 is the MSB most significant bit and Dn is the least significant bit. And ADC usually has two additional control lines. The start input to tell the ADC when to start the conversion, and the EOC end of conversion output to announce when the conversion is complete. There are three types in ADC, three major types. First one is dual slope type. Figure shows the functional diagram of the dual slope or dual ramp converter. The analog part of the circuit consists of a high input impedance buffer A1, precision integrator A2, and a voltage comparator. The converter first integrates the analog input signal VA for a fixed duration of 2 power n clock periods as shown. Then it integrates an internal reference voltage VR of opposite polarity, that is minus VR, until the integrator output is 0. The number n of clock cycles required to return the integrator to 0 is proportional to the value of VA averaged over the integration period. Hence, n represents the desired output code. Before the start command arrives, the switch SW1 is connected to ground and switch SW2 is closed. Any offset voltage present in the A1, A2 comparator loop after integration appears across the capacitor CAZ until the threshold of the comparator is achieved. The capacitor CAZ thus provides automatic compensation for the input offset voltages of all the three amplifiers. Later, when SW2 opens, CAZ acts as a memory to hold the voltage required to keep the output offset nulled. At the arrival of the start command at t equal to t1, the control logic opens SW2 and connects SW1 to VA and enables the counter starting from 0. The circuit uses an end stage ripple counter, and therefore the counter resets to 0 after counting 2 power n pulses. The analog voltage VA is integrated for a fixed number of 2 power n counts of clock pulses, after which the counter resets to 0. If the clock period is T, the integration takes place for a time T1 equal to 2 power n into T, and the output is a ramp going downwards. The counter resets itself to 0 at the end of the interval T1, and the switch S1 is connected to the reference voltage minus VR. The output voltage V0 will now have a positive slope. Now T1 equal to T2 minus T1 equal to 2 power n counts divided by clock rate, and T3 minus T2 equal to digital count n divided by clock rate. For an integrator, delta V0 equal to minus 1 by RC into V of delta T. The output voltage V0 will be equal to V1 at the instant T2 and can be written as V1 equal to minus 1 by RC VA into T2 minus T1. The voltage V1 is also given by V1 equal to minus 1 by RC into minus VR into T2 minus T3. So VA into T2 minus T1 equal to VR into T3 minus T2. Putting the values of T2 minus T1 equal to power n and T3 minus T2 equal to n, we get VA of 2 power n equal to VR of n. So from this, when we simplify, VA equal to VR into n by 2 power n. The main disadvantage of the dual slope ADC, analog to digital converter, is the long conversion time. Dual slope converters are particularly suitable for accurate measurement of slowly varying signals such as thermocouples and weighing scales. Next we have successive approximation type. The successive approximation technique uses a very efficient code search strategy to complete the n-bit conversion in just n clock periods. An 8-bit converter would require 8 clock pulses to obtain a digital output. So this is the functional diagram of the successive approximation analog to digital converter. The circuit uses a successive approximation register called SAR to find the required value of each bit by trial and error. The circuit operates as follows. The arrival of the start command, the SAR sets the MSB D1 equal to 1 with all other bits to 0, so that the trial code is 1 0 0 0 0 0 0 0. The output VD of the DAC is now compared with analog input VA. If VA is greater than the DAC output VD, then 1 0 0 0 0 0 0 0 is less than the correct digital representation. The MSB is left at 1 and the next lower significant bit is made 1 and further tested. However, if VA is less than the DAC output, then 1 0 0 0 0 0 0 0 is greater than the correct digital representation. So reset MSB to 0 and go on to the next lower significant bit. This procedure is repeated for all subsequent bits one at a time until all bit positions have been tested. The digital to analog output voltage is seen to become successfully closer to the actual analog input voltage. Hence it requires 8 pulses to establish the accurate output regardless of the value of the analog input. Finally, we have the flash type analog to digital converter. This is the most expensive technique. The figure shows a 3-bit A to D converter. The circuit consists of a resistive divider network, 8 op-amp comparators and 8 line to 3 line encoder, that is a 3-bit priority encoder. So this is the comparator and its truth table. A small amount of hysteresis is built into the comparator to resolve any problems that might occur if both inputs were of equal voltage as shown in the truth table. At each node of the resistive divider, a comparison voltage is available. Since all the resistors are of equal value, the voltage levels available at the nodes are equally divided between the reference voltage VR and the ground. The purpose of the circuit is to compare the analog input voltage VA with each of the node voltages. So this is the typical truth table of this type of converter. And now the circuit has the advantage of high speed, as the conversion takes place simultaneously rather than sequentially. Typical conversion time is 100 nanosecond or less.